Okay, guys. Oh, jeez. Where is the... I need to go find out something real quick. Facebook, okay. Okay. God, leave me alone. There we go. See, oh. Oh, jeez. Edward Mitchell. Poor guy. I feel sorry for him. Okay. I was looking at something on Facebook. I shouldn't be here. I did. Get on! Stupid. I hate Facebook. Close this window. Get out of there. Okay. Whew. I made it out. Okay. I was trying to find something, but I'm gonna actually just make this smaller so we can see more of what I'm doing. I do want the full scope shot in there though. Okay, before we even do anything, I'm gonna go ahead and do a few things here for fun. Oh, I guess I need those. I'll take the other ones off. Do I have 4 of these? I think I have 4 of these big probes. I'm going to take the current probes off. They're doing nothing for us at the moment. Unfortunately, they're out of my frequency band. I guess I got something new to buy though. I will order some high frequency current probes so we can get to the bottom of this. How about that? So now, I have to find those probes. Right, now those are the empty boxes, so I'll just use these. I'm not going with high voltage here, we're talking very low, so I'll just use these. They're already color coded correctly. So we got blue. Alright. Okay, we got blue. We need to make sure this is set on voltage, and these are times 10. Right. I thought the other ones were higher than that. Oh, yeah, they're times 100. Yeah, okay. So, whoops. What? There we go. Why are these? Okay. They're all the same. Okay. Let's hook up our signal generator again. No, it's already hooked up. Channel 1. Let's go ahead and punch in 1 megahertz. Okay, so now we got all these on here. So now what we're going to do is we're going to measure here. We're going to measure on the other side of the resistor. Can you guys hear me talking to myself? I'm talking to myself sort of out loud, but I can't tell if you can hear me talk under my tongue or not. That's kind of funny, actually. Okay. So this is a cluster of stuff, but this is what we got. We just want to take a couple of quick measurements. I want to see what it looks like. Okay. Why is this so screwy, huh? Center all these bad boys. Alright, so technically we're taking I want to go sweep these real quick. I just want to see what happens. I think I need to... Oh. 3 is like... Where's 3? Man, it's way out of whack. That's... Three's across. Huh. That sure is interesting. Okay. Okay, I gotta fix the trigger. The green. Let's put it on 2. It's so much cleaner. I'm not sure. Okay, something feels wrong with channel 1. Channel 1 is yellow. We have the yellow one here on the input resistor. That's why it's so small. Amplitude, this needs to be at 20. That's part of our problem. Offset 0, phase 0, frequency. Okay. Wow. You know, something doesn't feel right with this scope lead. It should not look like that, in my opinion. Just don't think it should be looking like that. It's a good connection. I think it was because I had the frequency turned up so darn high. So here's the deal. Tin Man, I asked him specifically what he wanted me to measure, and now I gotta go look. click on there and get to that. Yeah, alright. Alright, so I asked him where he wanted me to measure. Oh man, that's loud. Blah blah blah. My scope be what it is. Oh, I gotta go back.
Here, where you must use power factor. Scope channel grounds. One side of your resistor. One channel of your scope will go across the resistor.
Wait a minute, I missed it.
One side of your current through a resistor and the voltage across the inductor resistor combo. So Russ, if you wanted to demonstrate where you must use power factor.
Now that's not what I want. I just want to know
Scope channel
what we
ground.
talking about. I need to write it down.
Combo. Then you will see your phase variations between current and voltage, and that is when you must take into consideration power factor. So if you wanted to do that with your 4-channel scope, 2 grounds will go here.
Why does he have positive, negative, positive, negative? He's got it really, really marked. Let's see, this would be. He's got that marked a bit funny. Why does he have that marked that way? Okay. Here we go.
On 2 of your channels, 1 ground from each channel on here.
Alright, I'm going to set it up like he specifies just so I can say that I did exactly that because I offered to do that. Mess, huh? Why would I turn that off before I blow it up? Alright. Get out of here, all of this. Okay. So we got ground.
One channel, one scope probe will go across the resistor, the other scope probe will go across the resistor and inductor.
Yeah, so channel 1. Channel 2.
On your other 2 channels, the same thing, both your ground.
Yeah, okay. Just for you, Tin Man.
Here, one probe across the resistor and the other probe across the resistor inductor.
That's not really going to help me,
4 channels, and you can
but I'll do it
watch
anyway.
at the same time everything that is happening across our series circuit in this coil.
Because that's not
Scope being what it is,
how I would measure
you
it.
should be able to then do some math calculations for L1 and R1 plus R2 and L2 separately.
I don't know if I can do
you should
that.
take into account should take into account power factor. And you will find this one here is going to be dissipating a whole lot more power than this one here.
I don't know if that one's true. So I have to figure out how to set that up. Because I don't think I can't do the power factor on here unless I measure the current. But just for fun. Okay. Let's just hook this up the way Tin Man wants to see it. However, it's not going to be very helpful. Could try to use a 1 ohm resistor and do actual current measurements, but I'm not sure if I have any of those here. Alright, let's turn this thing off. Ink. Okay. Voice beeping at me. Well, the stream is going silly. Probably because I'm on the video. Alright, he wants both the channels of ground here. This is yellow. Okay, this is one. Alright, then he wants measure from here to the other side before we get to the resistor. Okay. And then the same thing on these two channels. But I'm not going to be able to measure the current properly. But let's just see what the signals look like. Okay. What a mess of stuff. Alright, let's turn this on. Okay. So I could do the calculations. I guess I could fake it. So technically channel 2 is taking a measurement across... No. Oh, channel 1 would be... Well, I need to switch those channels around. Because if I do a power analysis, it doesn't quite work like that. It does not work that way because of the way I've got. I mean, I'm gonna just fake this for a second. Just for fun, but I think I have to switch these channels around. So let's do this. Let's put this back on voltage. Yes, it's 100. I'm gonna have to rewrite this. This is gonna have to be channel 1, which is voltage. I'm sorry. Channel 2, and this one would be channel 1. Okay. 2, 1, 4, and 3. So That makes no sense. Let me think about this for a second. Oh yes. Okay. Measuring current and voltage. That's not exactly right, in my opinion, but my mind is pretty tired right now. And then 4. Power analysis. Application. Haha, that's actually not true. Okay. Does anybody remember what frequency I was using whenever I saw my interesting results? I have to go back and look at my own video. See, I didn't pay much attention to the frequency. I paid more attention to the I think we have to go up. Just gonna go up until I see, let's see. I want to see the minimum amount of input. I don't know. That's quite true though. Wow. So we have twice as much reactive power at this particular setting across the way. I don't think this measurement is exactly the right way, but yeah, I didn't. So, I mean, the whole reason I brought up power factor is because, yeah, exactly, he needs to measure the whole circuit. So I asked him what he wanted me to measure. I'm trying to measure what he wants me to measure, but I don't think I can quite do what he wants because technically this should be correct. I'm measuring current across two resistors that should be equal. I didn't check them, but they're both actually precision power resistors, so I bet they're pretty close. Oh, you know what? Oh yeah, it's hard to tell if that's a 0. No, it's a 0. Okay. It almost looks like a 108, but no, they're both 100s. Oh man. So, okay. Well, let's do, I can only actually view one thing at once. Let's just go fast here. Let's see. Go back down You know what I need to do though? I need to look and see exactly what frequency that sweet spot was on my own video. It's pretty funny, and I don't remember. Okay, let me go back. Why is my internet broken? You guys are still on here, so it should be connected. A copyright claim was blah 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 on your video. Of course it was. I was playing freaking music, man. It really won't load. There it's going. Alright, where is the sweet spot? Okay, it is right around 837 kilohertz. 837. So I want to put this on 837. And measure this. Right? And actually, that's exactly right. So you know what would be really interesting is instead of resistors I had light bulbs, but finding two identical light bulbs would be very hard. He was saying there's more power dissipating across R2 and L1 and R1 and L1. However, this specific frequency is not true. It's like identical. But what would be really cool is let's get an LED. If this is true, like right now, exactly the way I'm measuring it, that would be quite interesting. Because that just screws everything up. So if I can light, I need to take out the resistors to do this, which is a pain, but no. He lit an LED with the resistor in place, right? Yeah. Yeah. So where in the heck are my LEDs? I thought all my stuff is back at the shop. I should have an LED here. Alright, here's an LED. Let's find me a different one. This one's not bad, but it's got a resistor screwed. Oh, it's just sitting on there. Alright, well, just for fun, here we go. Okay, we can light it there in both directions. Then we should be able to light here because I'm seeing the same measurement across both of these. Yeah, there's like the exact same amount of power there. Now, what I do need to replicate, which actually let's do that. Let's just stick this LED on here. You know what I need to do? I need to turn off. Let's go back to measure. Let's turn off the quote current probes. So I'm measuring yellow, which is 1. Okay, channel 1 is here. It's across the resistor. Okay, and then also the blue. The blue. Okay. Wait, I'm sorry. No, the pink. Okay, good. So that's exactly what I have. So I want to go to measure. I want to make sure I get the same. Now I don't get the same. Why am I not getting the same? That's a bit strange, huh? Well, let's go find this so-called sweet spot, which I should be able to get here. So what'd you think of Joel, Dyden? Pretty cool guy, huh? He's a nice, really nice guy. Really nice guy. Alright, now we're measuring this weirdness. Okay, nothing there. And also nothing there. Okay, can't get this LED to light on either one of those. My coil's different too, though, you know. Are you home now, Dyden? 'Cause I'm free. Come on, I should have just a long lead LED in here somewhere. This one's not really the best choice. Joe was awesome, super kind. He's a really great individual. I'm working on a project with him right now, but unfortunately I haven't spent much time on it, which I feel a little bad about. But I'm trying to get a few other things knocked out of my way, and what we're working on isn't tremendously important, and I have my own thoughts about it. So, look, I can't get this to light at all, but I'm at a totally different frequency now. Let's disconnect this ground. And this ground. Oh, you know what part of it is? I'm triggering on channel 2, which isn't on. Actually quite confused why these just don't look very steady. Okay. Let's go to measure. Now I can't get anything here. I can't get this LED to light at all. Okay, I'm gonna plug back in the grounds and make sure they don't do anything stupid, which seems like they are. Is this? Oh man. I sure hope that this particular probe is isolated. I know the other ones are. I know for a fact, but let's go make sure this one is. Kind of concerned now after seeing that. I know the other two channels are isolated from each other. Alright, so this is a oh, you know what? It's not the probe. It's the scope. So the probe doesn't matter. Let's hook up, let's disconnect the green one. It's definitely changing, but I think it's just the capacitance. I really do. Put this one on this side anyway. Hold on. Green channel is 4. 4 is supposed to be from the center, which is this one. The blue one is supposed to be here. Well, it's definitely changing things, which is a bit of a problem. I have the current probe across this resistor, yeah. But right now I'm just measuring voltage. I want to see, I wanted to see if I could light this light. So now if I turn the current back on, there's your current. So if we go over to the application, go to power analysis, okay, the input is that. Let's just switch over. And the output is that. The thing is I don't know if I can trust these measurements measuring across a 100 ohm resistor like this. I think I need to measure across like a 1 ohm resistor. So I don't feel comfortable about the way that these are. I mean, 1 volt across 100 ohms, is that 100 milliamps? Well, the thing is I can't get my LED to light. Surely there's a freaking LED right here that has longer leads than that one. Those are not regular LEDs, are they? These have the chips in them. Actually, this white one is. This white one's a regular LED. But I thought white is actually harder to light up, right? But this is a voltage measurement, sticking an LED across this thing. Plus this is like a high-powered LED. Like a 3-volt one or something. Those are flashing LEDs. What are they? 3.4, 3.6 volt LED slow change. Yeah, these are my color changing ones. Well, I don't feel comfortable publishing a video on this until we get it a little more understood. And I don't think I have any. I should have some 1 ohm resistors in here. I think these are power resistors, but I think they're 2 straps in there. They might be wound properly. 5%. That's huge. I don't think that's a good idea, huh? Those are power resistors anyway. Everything I have is like probably 5% or something. Well, what do I do with that? Can't do much. I mean, the only thing I can do is put this back at our sweet spot. Okay, which 34 milliwatts. Let's think about this. If I have 100, okay, that's my voltage. My brain hurts, man. I'm very sleepy. Would that be times 100? Let's go back and look. I have these set right here. Current 200 milliamps per volt. Man, my brain hurts. If I have a 100 ohm resistor and I have 1 volt, that's 100 milliamps, right? My head really is not feeling great today. So that means that this would be half that. So 1 amp per volt. I definitely don't have 1 amp per volt. So if it's 200 milliamps per volt, what size resistor do I need? Are you guys listening? I'm very tired. .01 amp for 1 volt across the 100 ohm. So that's 10 milliamps. 10 milliamps equals 1 volt at 100 ohms. Because right now I'm measuring 200 milliamps per volt. So would that mean I'd need a 2K resistor? Wait, no, I need a 200 ohm resistor, yeah? I probably don't have a 200 ohm resistor. Let's just see. Well, maybe this is the proper range, but look at that. That's actually a precision one right there. 150 ohm. Well, let's see here. Well, my thing is I have to agree with what my scope agrees with. It's just not that easy, unfortunately. Red, black, brown. I doubt I have them. Wait, these don't even look right. Oh yeah, they do. These are 180. Okay. And also 150. Alright, well, let's try the next option. The next option is 1 amp per volt. What would that be? That'd be 1K. Yeah? 1K? 1K. brown, black, red. Now these are not precision resistors, but let's just see what happens. Did I get that right? Brown, black, red. Okay, that's 1K. So 1 volt across 1K. 1 amp. Wait, I'm going the wrong way. 1 amp per volt. Wait, am I thinking through this right? No, I can't go to 100. I can only go to 200. Won't let me. So it's 200 millivolts per amp. Wait a minute. Oh, okay. $200 millivolts per amp. Let's go back to the application and see if that's wrong. I think that's... yeah. That's too high. But you know what? It's okay. It's just a factor of 10, right? 5 volts per amp. Scale. 200 millivolts per amp. Or 5 amps per volt. 200 millivolts per amp. Wait, I was supposed to go to 100, right? So 100 millivolts per amp. That's what you want. Whoops. Dang it. No. Stop it. Okay. There you go. Okay, that is right actually. It's just a factor of 10. This is okay. This is okay. It's a factor of 10. We just have to remember it's a factor of 10. We got question marks all over the place. Let's put all these back in the middle. So we can crank them up. Basically, you just have to move the decimal place over and then we're okay. That is if the resistors are both the same, and it's kind of hard to tell, to be honest. There, we got rid of our question marks. Okay, so I'm doing this test for him because he thinks we'd see more and less. At this point in time, that doesn't hold true. Let's keep going. Our sweet spot was like right there, okay? It's identical. That's kind of funny. Alright, let's go to measure and make sure we got the same results. See, we don't have the same results. Why is that? Why is it different? We don't have any, we didn't change anything. But yeah, we don't have the same results. Maybe our probes are changed? You know what I'm saying? So if I just totally disconnect this channel and this channel, just completely disconnect them. Okay, we don't get much change because I think it's still the capacitance across the probes, right? But if I disconnect them here, and I disconnect this one here, wait a minute, I know why. So I have these set up differently now. I moved the channels around. Okay, so I have to look at... Aha, okay, this is why. So yellow, let's cross this resistor. And 3. Wait, that is the same. What the heck is going on? Do I have these backwards now? I'm very confused. Wait, I'm in kilohertz. Let's go look at my video again. Oh shoot, that was megahertz? Or was it? Let's see where we were. 2.5 megahertz. I'm sorry. Screwed that up, didn't I? 2.5875. There we go. Now we're in our hot spot. Okay. And I should be able to tune that. I'm just gonna tune this until I get a till I get my 300 millivolts, because I think oh, that was even lower. Look at that. Turn this up. I don't think it's getting a very clear okay. Now just for fun, let's see if I can get the LED test to work. No lighty. No lighty. I cannot get no lighties anywhere. Doesn't really mean a whole lot, except it doesn't work. Alright, so fine. Now let's go do our power measurements. Okay. So I have to refresh my own brain here, thinking about reactive power versus true power. Voltage is too low. He had 2.8 RMS on the middle resistor. Yeah, my coil's different too. So by request, alright, this is I'm just going to write these down. It's channel 3 and 4, so that's this one. So we have about 500 milliwatts. Well, wait. We have to multiply this by a factor of, what did I say? 2? 300 millivolts, so that's 3 milliamps, is that right? I mean, yeah. Let's do that calculation. I'll go back to measure. So 308 millivolts. Oops. Dang it. .308 divided by 100. 3.8 milliwatts. This is, again, a DC measurement, right? And then the other one is 1.12. So 1. Oh shoot, I screwed that up, didn't I? Or did I? 300 and... Are you still watching, Dylan? God help me. Okay, I'm just very tired. So 0.307 divided by 100. Why didn't it put the point? I have to put a 0 first, that's stupid. .17. That is correct. Okay. So then to do the same calculation, I'm going to take 1. Where are we at? 1.22 and divide it by 100. Alright, and that's 122 milliwatt. Okay. That makes it confusing. What time is it? Almost 11. I'm going in after these measurements. Okay. So now we're going to switch to the power analysis application. Okay. This is R2 and this is R1. Okay. So it says true power. We'll call it 450. It's bouncing all over the place. 440. Now, this is a factor of, what did we say? 10? So, if it is 440, then it's actually, wait, if it's 440 milliamps, so it's 0.440, and then we divide that by 10, so it's 44. Oh no, it's 100. We decided it was 100 earlier. So right now I'm on 100 millivolts per amp. So technically that'd be 4.4, right? Or is it 44 milliamps? Reactive power. Reactive power. 1.8 VAR. But we have to multiply that. Dang, I hate this. Still with me, Dyden? 44 milliamp. Okay. So you think it is 44 milliamp. That's from the coil too. Actually, it's milliwatts. Milliwatts, not milliamps. But then, like the reactive power, if we're talking 1, okay, we're moving the decimal place. 1, 2, 3, 4. What the heck? I hate doing these calculations. I really, really, really do. You know what I'm going to do? I'm going to write them down as they are, and everyone else can do the darn calculations. So right now it's 440 milliwatt. Reactive power is 1.06, and this is in VAR. I read about this a while back, and I forgot exactly. Okay, power factor is 0.38. 0.38, and we want it closer to 1 to have good power factor. And then phase angle is what are you trying to calculate exactly? So, oh, here, 10 milliamps is 1 volts times 100 ohms. 10 milliamps. So I'm a factor of. So here's what I'm saying. Hold on, let me write down these measurements just real quick. Okay. Here we have. We're going to call it. Man, it's too close. This is too close to tell. Hold on, I want to change the trigger over to channel 2. There we go. I have no idea why it's having such a hard time. Let's go make sure these are still the same. Yeah, those are pretty well the same. Let's go look at these. So we have about, man, it's bouncing all over the place. I'm going to call it 500. Now he said way more power. I better pronunciate that right. Now the thing is the reactive power. The reactive power is different. It's 4. Power factor, though, is 0.1, which is actually worse. We actually have a much worse power factor. And then the phase is about 82. Let's go back and measure this. Hold on, I'll ask this question again. I'm trying to get an answer for. So 67. Okay. So, look, right now I am measuring technically 308 milliwatts in a DC calculation. That's across that. I can't do that the same. Okay. So look, are you listening? Alright, I'm going to go back here. Okay, my probes are set to 100 millivolts per amp. Okay. So the scope is set to 100 millivolts per amp. Current probe. Okay, so I'm set to 100 millivolts per amp. So therefore I do no calculations. It is exactly 440 milliwatts. There's no factor of anything, right? Oh, wait, yes there is. Because this is 10 milliamps per volt. Okay. 10 millivolts per amp. Right there. I can do that. 10 wait a minute. It's 10 millivolts per amp. So that would be a factor of like 100 or 1,000 actually. Let's go back. So if I set this to 100 millivolts per amp, okay? 100 millivolts per 1 amp. So right now, the way I've got it set up, it's technically 10 milliamps per volt. Oh, see, this is amp. That's why it's so confusing. Okay, I got it all backwards. So this is currently set up for 10 milliamps, and that's currently set up for 1 amp per 100 millivolts. So I get so confused right now. So I'm just trying to figure out the scale. This is what's real, 10 milliamps per volt at 100 ohms, and what my technical settings are on the scope is 100 millivolts per amp. So what's my calculation? I think I'm going to make a quick video of this. Okay, and then I'm going to call it a night. I'll probably post this. Tip of the day. Lack of sleep screws you up. Bingo, you said. What? Is it correct? Everything is skewed by 10. So 10 milliamps times 100. I would sleep on it. I think I'll record the video because I'm in the zone of thinking about this. But then I'll maybe wait to publish it. I'll let you guys watch it, see if I screwed it up. But look, 10. Oh shoot. Hold on. Point. Why do I have to punch the 0 in first? 0.10 times 100 is 10. So it's actually times 1,000. Wait. Times 10. 0.1 times 10 is 1. Now I'm even more confused. That's okay, I'm going to film the video, and then I won't publish it. Shut my door. He's yelling across the room. Alright, where's my camera? Let's try this. See how the lighting is in here. It's probably fine. It's kind of high light. Hello. Mic is on. Okay. Alright, here we are. So I asked kindly Tin Man, what would you like me to try with my 4-channel isolated oscilloscope? Now, I think it was eFinder who said, is my signal generator ungrounded? And I actually don't think it is. I have to check that. But I may edit this out. Okay. Alright, so we're going to find out exactly what Tin Man wanted to find out. So here's the setup. R1 has channel 2 because I have to use it as current. Channel 1 is the voltage, or I'm sorry, channel 1 is the voltage across this whole entire R1 L1. Okay. Voltage current. Okay. Then channel 4 is the current across R1. Channel 3 is the voltage across this. Now, Tin Man said that there should be less power consumption here and much more power consumption across these two. Okay, so that's the setup. So let's go up here and look at the measurements. Alright, I want to show you the scope is, the output here is 2.95 megahertz, which is really close to what we had previously. And as you can see, we've got channel 1 at about 300 and something millivolts across R1, and channel 3 is about 1.25 volts. Okay, so it's exactly what we had previously in my last video. This time I'm using the resistors as current probes. Okay, they're both 100 ohms, so we can figure out the current flow between backwards. Before I go on, because I'm just blibber blabbering, I moved the scope leads. Right now I'm measuring across the inductor, channel 1, which is the yellow one here. Do I have all this screwed up? Now I need to double check everything. Alright. No, I do have this right. Except, okay, that's part of my problem. We're measuring current, so we need to go here and change this to actually channel 2. And we need to change this to channel 4. There we go. Now it says amps, but that's a voltage measurement across the resistor. Now I'm with it. Dang. I do need to sleep on it. I think I will, but let me check something. Let's check what my frequency was and get back on there. 756 kilohertz. Huh. That's where I'm at. Right there. Buffering now. Oh, sorry, it's because I was probably on my video. Sleep and forget. Might have to. But what's weird,
Just over 300 millivolts input.
yeah, it's like 770. Okay, fine, I'll sleep on it, but let's think about this real quick. I'm measuring current, the blue channel, and then I get all these mixed up. You know what, here's what we're gonna do. We're gonna take all these off. We're gonna start over. Nothing wrong with that. Okay. So we're gonna follow my map because 2 is current, 4 is current, 1 is voltage, 3 is voltage. So R1 is this guy. It's gonna have channel 2 across it. Okay. Channel 2 across it. So from ground, channel 2. I think I had all this messed up. Okay, channel 2, alright, and channel 1, yellow one. This will fix our problem. We'll get accurate measurements here before I go to bed, because now it's going to bother me if I don't, even though I'm exhausted. Alright, so we're going to take this and also measure current. We're measuring voltage, okay, not across that resistor, just across, actually across this one, yeah. Right? No, we want just that resistor, just this coil. Yep, okay, perfect. Next, channel 3, actually let's do channel 4. 4 is current, 4 goes across the resistor. We're going to call this ground. Okay, we're going to call this a current measurement. We're going to do the same here. This is going to be considered ground. Kind of like to get it over on there, but okay. Alright, and this is going to be a voltage measurement. Ah, okay. Now, let's go back to our power analysis. Just see how things are. Okay. Same exact power factor between channels. Phase angle is almost identical. True power, 1.32 watts across this one, the first one, between R1 and L1. And this actually needs to be adjusted. Let's go back and make sure that's right. Oh, okay. It was screwed up because I was too high. Start over. See if I get this way out like this. Look at that, screwed everything up. Try again. Alright. No question marks. Now we're getting the right measurements. Alright. True power, 4.4 watts, which is 4, or times, I still think we're times 100. That would bring us down to 4 point something. Oh, yeah, but we're talking the whole circuit, so it's different. Okay, whatever. And then channel 3 and 4. Okay, it's the exact same. There's no difference. So you know what I'm going to do? I'm going to tear off this paper. I'm going to use this as my reference. I'm going to make this. Set the trigger better. Trigger's great. I don't need to change anything. Okay. Now we get an identical power measurement. Let's go back to measure. Now what's weird is why we don't see this ginormous difference in voltage. That I don't understand. However, the probe, the blue probe, which is current, right? If we change this back to voltage, and we change this back to voltage, and we go back to measure, we don't have the same values anymore as we did the day before. Now we can get an LED light up. Okay. Now I'm going to adjust my frequency till I start to see anything interesting. There's our interesting point. Right? Okay. And that is about this. Holy crap! The frequency's all over the place on my screen. Oh wait, this is why. I need to adjust teal channel up. It's too small. Here we go. Now let's see if we can get this LED to light and not light. Not light. Still not light. But earlier I was able to. But we want to pay attention to the scope. We don't care about this LED right now. Right there is like perfect phasing between the teal, which is 2, and the purple, which is 3. Perfect phasing between 3 and 2. Inductance. No. R1 and L2 is perfectly in phase. The other two are out of phase. Okay, so this should be the right measurements. This is what we saw before. Now let's change this back to current. Okay, I should do this on the video as well. Current. And then we're going to change this one to current. And we're going to go back to measure. We should see this, the resemblance in milliamps. There you go. 310 milliamps. Actually, that's a proper measurement, isn't it? We don't have to do any math. Oh wait, no. It was 3 point something. Alright, let's just go back to the application and see where we're at. Just for fun, okay? Okay, pumpkin? Okay. Lost internet. I'll be back. Looks like it's a total flop. Wait, do we do the, let's see, 2, let's go back to measure. I want 2 and 4, which is my resistors. Okay. And then here it's like totally screwed. I need to look up what VAR stands for again, 'cause I forgot how to think about that measurement. Reactive power. Volt ampere reactive. What is VAR in engineering? I should go read the manual on this oscilloscope and not read the freaking Wikipedia, but... Okay, apparent power. Imaginary part of apparent power. The power following into reactive load where the load and current specify volts and amperage, two definitions equivalent. Yeah, okay, so that's what I thought. So it's basically the apparent power, which is the non-real power, right? Yeah. I should not talk about anything that I'm not really clear on, because it's been a while since I've looked at this. But that's exactly what it is. Apparent power, right? Is that correct? Am I thinking of this correct? Apparent power is conventionally expressed as VA, since its unit is by reactive power, volt amp reactive. Apparent power is closer to real power. Apparent power, what? You just put two things together that don't go together. Apparent power and real power. Real power is true power. True power is not apparent power. So now you've got me totally lost. Sorry. But yeah, no. Let's read up on this before I make this video. We know that reactive We know that reactive power such inductive capacitors display zero power. Yet the fact that they drop voltage called this is impression that they actually do dissipate power. This phantom power is called reactive power. It is a measurement of unit called volt amps reactive, VAR, rather than watts. The mathematical symbol for reactive power is unfortunately the capital letter Q. The actual amount of power being used or dissipated in a circuit is called true power. Okay, so it is apparent power. And the measured order watts. The combination of reactive power and true power is called apparent power. Ah, the combination of reactive power and true power is called the apparent power, and it is a product of a circuit's voltage and current without the reference of phase angle. Apparent power is measured in the volts of volt amps and symbolized in one capital letter S. A rule, true power is a function of the circuit's dissipative elements, usually resistance. Reactive power is a function of the circuit's reactance. Yes, apparent power is a function of a circuit's total impedance, the Z value. Okay? Yes. Since we're dealing with scalar quantities of power calculation, any complex starting quantity of the voltage impedance represented polar Gallic resistance, imaginary. Okay. I must use the polar magnetic quantities. But you know what? I can tell you right now that we have a low reactive power and a high true power, and if we look at our true power factor, it's closer to 1, which is what we want. Anything closer to 1 is real power being consumed. This I know for a fact. Yeah, I know what Tin Man's thing was, and I don't have any light bulbs here right now. I'm not going to demonstrate that. I told Tin Man, what do you want me to see? Or what do you want me to do? What do you want me to measure with my 4-channel oscilloscope? That's what I'm doing. That is what I'm doing. I'm doing exactly what he wants me to do. The weird thing is the measurement is different than what I had last time. Let's watch my video a little bit more. I got the door closed. Yeah, right there, 3.4 megahertz, and we're at 3.5, so it's exactly the same frequency. Command boss. Now this is fun, man. I'm loving this. I really am, because we're all learning something new here. And you know what? It's nice to see, what we're seeing. True power closer to 1 power factor. I just want to make sure I got my thinking right. Reactive power, apparent power. So the delta, interesting. Real power is a straight line on the bottom. Apparent power is a delta function. And Q, the reactive power, is the measurement between those two. Okay, that makes perfectly good sense. So decreasing the power factor. Let's go back up and read this real quick. Definition of power in watts. Reactive power is Q, blah, 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 blah. I just want to know about the further we get away from 1 here. Okay, the power factor, cosine 0, or the cosine, what is that, theta, increases the ratio of real power, apparent power, which is cosine theta, increases apparent unity, approaches unity, 1. While the angle decreases, the reactive power decreases as theta, 1. Theta is closer to 1. The maximum possible value is theta is to 0, so Q is 0. Oh my gosh, that's a little confusing, but this is actually a nice way of describing it. Okay, when power factor is equal to 0, the energy flowing in its is entirely reactive, and stored energy in the load returns to the source on each cycle, so it's not being consumed. When power factor is 1, all the energy supplied by the source is consumed by the load. Power factor usually stands for leading and lagging. A purely resistive load connected to a power supply current, the power factor will be 1, because it's being consumed. And the electrical energy flows in the single direction across the network. Okay. Although, go ahead and look in the attic. I have some at work. I was trying to say it's reactive power. That's the imaginary one. Yeah. Okay. This is correct. But let's see. I want a good literature to add to this video. As the power factor increases, the ratio to real power, apparent power, which is reaches unity, which is 1. Let's go find a slightly better, shorter description of power factor. But I really like these diagrams I'm looking at. I don't want to misspeak, but I definitely want to nail the point down, right? I'm okay with misspeaking. So basically, if we're looking at the circuit like he wanted to look at, I'm consuming more real power over here and almost nothing over here. And that's actually 100 milliwatts. And this one is actually, it's about the same. Wait. Maybe I'm confused. No, I'm not confused. Look, I'm just gonna make the video, and I'm not gonna go too much into the... You showed the power factor triangle. You showed the power factor triangle. Can you see my screen? I did. One has high power factor, the other has less. You showed the power factor triangle, one has high power. True power is the same throughout the circuit's entirety. Look, I'm just gonna film this as we see it right now. No, I don't have enough power. I'll get some at work. I have some micro light bulbs at work. I know exactly where they are. But I'm going to film this right now and be done with my adventure tonight. I just want to show what it is I have right now and leave it at that. I'm not going to make a bunch of assumptions and crap. I'm just going to make a video. Okay? Okay. I'm just going to make this video. I'm not going to make any claims. Actually, I need to change that to 2 and this to 3. Okay. So I need a screen capture. This, okay. I think that's fine. 4 point something. Oh, that's a bad shot.
There's your current amplification.
Oh, there. Now it's fine. 1 point volt, 1 point something. Okay. Wait, why does it say 600 and something megahertz? Now we're gonna get screwed up again.
Now what's important?
Oh, it's... There we go. It's okay. Now it's fine. It's the fact that it's flipping around. Okay, don't worry about it. I wonder if I got a better shot of this. Let's go see if I do.
Got some really nice. Just set the scope up. Now we're going in.
Probably not going to be able to get what I want. Yeah, maybe I can. Go find our sweet spot.
Let's go find our sweet spot.
Do it. Find it. Hurry up.
That sweet spot.
Oh, I wanted you to zoom in. Come on, Russ. What are you doing?
300
Get in there.
millivolts input versus our
There we go.
output.
Okay. I'm leaving it right there. Here we go. No assumptions. The scope is showing true power beyond the same cross resistors. Yeah, just let people see the numbers. Okay. Here we are. Okay. Alright. Here we go. Welcome back, everybody. So, I asked Tin Man, hey, what would you like me to measure with this 4-channel isolated ground oscilloscope? So that is what I'm doing. I'm going to show you exactly what Tin Man wanted me to show you. I'm not going to make any assumptions or claims because I want you to read the numbers and then you can do the math. You can figure out what's going on and you can tell me if what we're seeing is real or not. So let's do this. Alright, Tin Man, he wanted me to do this. He wanted me to measure R1 as a current and then R1 and L2 across both of these as a voltage. Then he wanted me to measure R1 as a current and R1 and L2 across the voltage. Now personally I think this is a little incorrect, but honestly it's so late at night I'm confused and I'm a little tired. However, what I'm going to demonstrate right here is exactly what he asked me to do. So I have channel 2 across to R1 and I have channel 4 across to R1, channel 1 across L1 and R1, okay, see the connection, and channel 3 across L2 and R1. Okay, so ground is here, and then for channel 1, channel 2, ground is here for channel 3 and 4. Okay, this is how he wanted me to set it up, so that's what I'm doing. Now, the reason that 2 and 1 are flipped here is because I have to use channel 2 as current for my power analysis software to work. So, what I'm going to show you, 10 Man, he told me in his response video that I'm going to see a lot more, a lot less power being consumed here, and a lot more power, output here. So less in, that's what he described it in his video. R1 and L1 is going to consume less, and there's going to be more on R2 and L2 over here. So that out of the way, you can go watch his video for what he wanted me to do. With that out of the way, I want to show you a quick screen capture of my previous video. So the frequency is just about 3 megahertz. It's actually on different screenshots, it's a little more. Alright, my voltage measurement, you got to remember I got channel 1 and 2 is flipped. So channel 1 and 3 here is flipped, not 1 and 2, but 1 and 3 is flipped. Now I'm using channels 2 and 4 as my current measurement. So I'm measuring across 100 ohm resistors. Okay, so that's the way I've got it configured, the whole thing configured. So I've got 362 millivolts across R1 and 1.28 volts across R3. So that's technically a current measurement across a 100 ohm resistor. Okay, so I've got the exact same thing set up here. I'm going to switch my hands here. I'll try to hold this steady for you because I want this to be clear. Okay, so what I've got is all voltage measurements currently, but I'm going to switch these probes. So channel 2 is across L1, channel 4 is across L2. You can see I have the equivalent numbers is what I have on my screenshot here. Alright, so we're at the same place, and I'm just over on frequency, but in my video I showed that this is actually a better frequency. I was just demonstrating something different there. So what we're going to do is we're going to go to channel 2 and we're going to switch this to current. It's on 100 millivolts per amp. So if there's any scaling to do, up or down, then you'll need to do that. Currently, it is scaled, I believe. So just remember that this is scaled differently. So the true power ratings later is actually going to be, the decimal place is going to be moved around, but the numbers are correct. Don't worry about the scaling, just know that they're equal. Okay, so I'm changing, alright, voltage to current. Alright, and we'll go back to measure, and we can see now we're measuring 314 milliamps. Alright, let's switch it back real quick so you can see this again. I'm going back to voltage, go back to measure. Alright, we have 309 millivolts. Okay, so it's an equivalent measurement, as it should be. Actually, I don't think there's a scaling here. Had to go over that a while in my head, but I'm really tired, so forgive me. Okay, then we're going to go to channel 4, and we're going to do the exact same thing. Actually, let's go to measure. Okay, we're at 1.35 volts. Okay, and let's go back to the channel. We're going to switch it over to current. We're going to go to measure, and it is 1.35 amps. Alright, let's go back and do it again just so you can see, because I think I had that wrong. Yeah, volts, okay, 1.34. Alright, back to current, and there we are. Okay, so now we can do power analysis. Okay, so I'm doing power analysis the way 10 Man wanted me to do it here. So we've got a measurement of voltage across R1, L2, R1, L1, okay, channel 1 and channel 3, and then we have current flowing through each one of these sections of the circuit. So here we go. Application, power analysis. So the first thing we're going to do is go to channel 1 and 2. Alright, so true power, alright, true power, this is the power being consumed. Reactive power, okay, I'm not going to go into detail here because I don't want to misspeak. Now, true power factor is 0.93, so closer to 1. Phase angle is 21. Okay, now let's switch it. Okay, before I switch it, these measurements, again, are here. Okay, these two measurements. So this is basically this half of the circuit. So now we're going to go and we're going to look at channels 3 and 4, which is the other half of the circuit. Okay, we have about 90 milliwatts. I'm sorry, 900 milliwatts, almost 1 watt, right? Now, our reactive power is 3.89. Now look at our true power factor. It's at 0.2. It's on the other side of the scale, all the way down to nothing, more towards 0. And the phase angle is 77, right? More towards our 90. So let's go back. Phase angle is 21. All right. Channel. I'll just let you look at the numbers. Here we go. Channel 1, true power 1.6. Okay. Let's do this repetitively. So here is the first half of the circuit. R1L1, 1.6 watts. R2L2, closer to 860, 900 milliwatts. Okay, let's go back. First half of the circuit, L1 and R1, reactive power, it's 470 milli VAR. Channel 3 and 4, we're all the way up at 3.8 VAR, not milli. Alright, go back to channels 1 and 2. True power factor, look at that, really close to 1, which is a good thing. That means it's consuming power. Alright, channels 3 and 4, back down to 0.2. True power, right there. So the power is within the circuit. That's apparent, or the opposite of true. It's actually a mixture of the two, but like I said, I don't want to misspeak here, so just you do the math, you look at the numbers. Now the phase angle, 21. That's on the first part of the circuit. Let's go back to the second part. 77. Okay, so like I said, I really don't want to misspeak, but I definitely want you to understand what I was trying to say in my previous video. Now, this is a bit different. So I think he may have mentioned a different way of measuring it, a second version of measuring it, and I'll do that. Right now it's really late. I'm going to just shut this thing down, but I wanted to show you the numbers. Okay, these are the numbers. That's the first half of the circuit, true power, power factor, important numbers, and reactive power. Second half of the circuit, there it is. So do some homework, guys. Read about power factor, understand how it works, understand how things work here. Understand the way we're measuring it here, because this is a bit screwy in my head right now, and I don't know why I'm thinking so funny, but it's almost, I don't know, midnight or something. And I've been up way too many hours working on all these projects, and I love it. So this is actually a lot of fun, you know. Me and Tin Man, let me set this camera down and turn the light on. Me and Tin Man actually started the, where's the hat? Me and Tin Man actually started the post-mortem build-off with a challenge for a whole different reason that I don't need to go into. And this is really the same thing, man. Me and him were just working back and forth, kind of argumentative-y. Is that a word? Anyway, and it's a lot of fun. I love doing this stuff because the thing is understanding how you measure, understanding power factor with AC, understanding what's happening in these coils is just crazy. Now, Tin Man is demonstrating a light bulb, okay? This is interesting. This is really interesting. He's demonstrating that on R1, okay, R1, no light bulb is being lit, and on R2, he can light a light bulb. Now, because it's a resistive load, okay, you'd think it'd be consuming power. Okay, but just look at the numbers here with the reactive power and understanding reactive power and how that works inside of a circuit. And don't forget, you know, R2 is in between these two coils, okay, which is an interesting spot. So anyway, that's all I got for you. Like I said, this is great. You guys can tell me what I did wrong or right, and hey, I'm glad, man. This is how we learn. We're teaching each other and we're learning. So we need to do this kind of stuff. Positive criticism, I take really well, and so let's have it. Do what you want. Game on. All right, peace and love, Tin Man, and everyone else out there watching. We'll see you on the next round. I'd like your video response on that. Might take a while for you to decide what's going on. I'm going to get some sleep, and I'll decide what the heck is going on tomorrow. Bye. Do 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 do. Okay. I think I'm satisfied with doing what Tin Man asked and taking the measurements I took, even though I think it's a little screwy, because I'm very confused. But we are measuring power factor across those coils. And we are having a phase shift, just as I was trying to tell him. Nobody wanted to listen. Now, what I'm interested in is people who are smarter than me. I want to see what they say about this. They may go, oh yeah, the Tin Man's right. It's amazing. And some people go, what the fudge settled? Alright, I'm sure my wife just texted me. She's probably like, what are you doing? Alright, love you guys. See you later. Thanks for helping me out, Dyden, and everyone else. Where's my mouse? There we go. See you guys tomorrow.